Hello students, in this module we are going to discuss semiconductor devices. Nowadays all the electronic devices which we use are based on controlled flow of electrons. Before 1948 mostly the electronic devices were made of vacuum tubes. In these vacuum tubes the electrons are provided by heating the cathode using low tension battery. In 1930, it was realized that some solid-state semiconductors and their junctions can be helpful of controlling the number and direction of flow of charge carriers through them. The discovery of semiconductor junction, that is, the junction diode and transistors, replaced the vacuum tubes as they are small in size, operate at low voltage, consume small power, having long life and high reliability. We have seen that the electronic devices is made up of semiconductor. Why this semiconductor is used to make electronic device? For that, we have to see the structure of semiconductor and what is its difference from conductors and insulators. We will discuss it on the basis of energy band diagram. See here, this is the structure of silicon atom. You know the atomic number of silicon is 14. So outermost shell 4 electrons are here. Outermost shell 4 electrons are here. See, you know that this is the first orbit and this one is the second and this is the outermost. In the case of an isolated atom, the energy of the electron is equal to the energy of the orbit. Here, the energy of the orbit is fixed. Why? Because it is an isolated atom. Here, we are showing the energy level diagram of an isolated atom. So, this is corresponds to first orbit, this is corresponds to second orbit and this corresponds to third orbit. Here it is showing by discrete line because it is an isolated atom. The energy of this orbit, it is discrete. When we consider this atom in a crystal, the energy of each orbit is not fixed. That is, we cannot show it by a discrete line. Here, the influence of neighboring electrons will come here. So, the energy of each orbit is in a range. So, here we are going to represent it in a bands. The range of energy possessed by electrons, that is called energy bands. So, but you know that outermost electrons, the influence from the neighboring atom is more. So, the range difference will be more for the valence electrons. So, here this is more thicker than the inner bands. So, what is energy band? Energy band is the range of energy possessed by electrons. So, what is valence band? The range of energy possessed by valence electrons. So, you can see here inside the crystal each electron has a unique position and no two electrons see exactly the same pattern of surrounding charges. Because of this, each electron will have a different energy levels. This different energy level with a continuous energy variation form what are called energy bands. So, range of energy possessed by electrons, that is called energy bands. The energy band which includes the energy levels of valence electrons is called valence band. The energy band above the valence band is called conduction band. So you can see here, this is the outermost shell, that is the valence band. Outer of the outermost shell, that is actually when by any type of energy we give to the atom, the electrons become free and it is shifted to the conduction band. So usually the conduction band is empty, but because of the energy variation, few electrons jumps from the valence band to the conduction band. In between the valence band and the conduction band, there is an energy gap that is called forbidden energy gap. The gap between the top of the valence band and bottom of the conduction band is called energy band diagram. You can see that conductors, the valence band and the conduction band is overlapping. Here the semiconductors, the gap is less, but in the case of insulators, the gap is more. Now we can differentiate conductors, semiconductors and insulators on the basis of energy band diagram. See here, this is valence band and this is the conduction band. Here the valence band and the conduction band overlapping each other. This is the case of conductors or metals, and here the energy gap is very less. So this both the cases is possible for conductors. A large band gap exists, that is band gap energy is greater than 3 electron volt. There are no electrons in the conduction band and therefore no electrical conduction is possible. This is the case of insulators. So you can see here, this is the conduction band. This conduction band is empty and valence band is filled, but the energy gap is greater than 3 electron volt. Whenever these electrons get energy more than 3 electron volt, then only these electrons will jump from the valence band to the conduction band. In the case of semiconductor, the energy gap is less than 3 electron volt. At ordinary temperature, few electrons get enough energy and it jump into the conduction band. At absolute zero, semiconductor acts like an insulator, but ordinary temperature, few electrons are in the conduction band, so it shows some conductivity. These electrons can move in the conduction band, hence the resistance of the semiconductors is not as high as that of insulator. In this section, we have made a broad classification of metals, conductors and semiconductors on the basis of energy band diagram. So we have seen that in the case of conductors, the energy band is 0, and in the case of insulators, it is greater than 3 electron volt, and in the case of semiconductor, it is less than 3 electron volt. Next, we are going to discuss intrinsic semiconductor. Intrinsic semiconductor means a semiconductor in its purest form. Usually, silicon and germanium we are taking as a semiconductor. Here, this is the crystal structure of germanium or silicon. Here we can see that these structure are called the diamond-like structure. Each atom is surrounded by 4 nearest neighbors. We know that silicon and germanium have 4 valence electrons. In its crystalline structure, every silicon or germanium atom tends to share one of its 4 valence electrons with each of its 4 nearest neighbor atom, and also to share 1 electron from each such neighbor. See here, this is the case of a pure semiconductor. Here, say this filled circle, it is showing the bonding electrons. Then this is the covalent bond, and this is the silicon atom or a germanium atom. Then what happens as the temperature increases, the electrons from this site, say this electron, thermally generated electron, the electrons left from this site and by leaving a hole here. So this hole is at the site 1, and you know that the electron become free. This is the free electron. then the vacancy of this electron, that is called hole. But you know that from the site 2, the electron will shift to this site 1 by leaving the hole here. That way the holes and electrons shift in the crystal, and that constitute current. But we can see that the number of electrons equal to number of holes. Here we can write the current due to electron is IE and current due to holes, that is IH. But the total current IE and IH will be in the same direction. So we can say that the net current I is equal to IE plus IH. Why? Because the conventional direction of current is in the direction of positive charge. Now we can see the energy band diagram of a pure semiconductor, that is intrinsic semiconductor. This is the valence band. Here see this valence band is completely filled. Say this is representing the electrons and the conduction band is empty. This is at T is equal to 0 Kelvin. As the temperature increases, what happened? Few electrons from the valence band jump into the conduction band. So the vacancy of these electrons, that is represented by empty circles, that is holes. Due to the thermal agitation, electrons jumps from the valence band to the conduction band. So here this is the case of the temperature is greater than 0 Kelvin. Now see the explanation. Here it is given that the recombination occurs due to electrons collide with the hole. An intrinsic semiconductor will behave like an insulator at a T is equal to 0 Kelvin as shown in the figure A. It is the thermal energy at high temperatures, that is T is greater than 0 Kelvin, which excites some electrons from the valence band to the conduction band. These thermally excited electrons partially occupy the conduction band. Therefore, the energy band diagram of an intrinsic semiconductor will be shown in the figure B. Here, some electrons are shown in the conduction band. These have come from the valence band having equal number of holes here. So, we can say that the concentration of electron is equal to concentration of holes is equal to Ni. So we can say that Ne is equal to NH is equal to Ni. So Ne into NH is equal to Ni square. Now we have one question. Carbon, silicon and germanium have same lattice structure. Why is carbon insulator while germanium and silicon are intrinsic semiconductor? The reason is that you know that these all the three elements, it belongs to same group. But the size of the carbon atom is small as compared to silicon and germanium. So the outer valence electrons are more bound to the carbon nucleus. So the energy required to leave the valence electron of carbon atom, it is more. So we are not using carbon in place of silicon and germanium. Here say the 4 bonding electrons of carbon, silicon and germanium respectively in second, third and fourth orbit. Hence the energy required to take out electron from this atom will least for germanium followed by silicon and highest for carbon. Hence number of free electrons for conduction in germanium and silicon are significant but negligibly small for carbon.